So a couple things that I have lined up, at least that I plan on talking about, are discussing a couple of the advanced and mechanical mates that we haven't really gone into too much depth about. Um, and there will be a couple of those advanced or mechanical mates that are present on the exam. So that's kind of why I wanted to include it. I wanted to also go through editing the bill of materials a little bit because I know probably not everybody wants to sit through the entirety of uh, that assembly drawing lecture just for when I go through the details of changing description to material instead, which is going to be important. Um, there's also a couple features in assembly that can be very helpful as well in terms of, or like regarding like the whole wizard, and probably just some details about bolts themselves. So kind of how to interpret uh, the different details that you see when you're given a bolt specification. What the heck does any of that stuff mean? And how can you translate all of those details into um, like the correct measurements, whether it be diameter or length, like screw length for that bolt itself. I think this might be about all that we're going to get for right now. So I might as well just get started. I am recording right now, so anybody that shows a little bit late can listen to that short 2 minute spiel that I just had. Um, so in terms of some of the mates that I think are going to be important. So I already opened up an assembly right here, so you probably are looking at some of these and recognizing them as being very familiar to some of the either assignments or homeworks that we've had in the past. So this was our like first in-class assignment 7, and these were two parts for the from the yoke. So we have the yoke and we have the adjusting pin here. So in terms of some mates that we could possibly use, let me just open up our mates menu. So by this point, most of us should be fairly comfortable with how a lot of the standard mates work. So parallel just means that those edges or faces are going to be parallel to each other. Coincident means that things are generally speaking touching. I like to think of coincident faces as basically being in the same plane. So if I say that I choose coincident and I choose this face and this face, well then if I hit select on this, then I can still move this around, but it's always going to be in plane or in the same plane as this face here, even when it's way the heck up there. But I don't necessarily want a mate like that. So I'm just going to get rid of that mate that we have there. In terms of advanced mates, there's a couple here that I haven't really talked about too much. Um, and a few that we have used fairly frequently. So things like the limit distance or limit angle, those are really good to make sure that there's only a specific distance that an object can move or a component can move, or only a certain angle that can be specified, or a range of angles rather than just putting, hey, I want it to be 40 degrees and never change from 40 degrees. I can say, well, maybe I want it to go from 0 to 40 degrees, something along those lines, where there's actually some variance in what it could possibly be. Um, I know I briefly showed you guys PathMate, and we really won't touch on that too much. That gets a little bit too much into sort of complex curves. Width is pretty nice because it allows us to it almost behaves sort of similar to like a limit distance, only you just specify the, basically the ranges where you want some object or some component to be, and you're able to keep something within that range. So perhaps maybe I wanted, it's a little bit harder in this example since I don't have much constraint, but perhaps I wanted some sort of small block to be confined between this face and this face here. Well, I would just select those as the width references, and now it says, okay, well, there's a distance of 48 millimeters between those two, which means that whatever the heck I select between them, I might be able to select one of these. Yeah, whatever I select between them, if I choose a free width, well then it's only going to be able to move in that range. You see when I kind of move it back and forth, that actually starts pushing the yoke just because the yoke is not fully defined yet. And even when it's not specifically touching the yoke, it's still moving it because it is constrained in the X direction. I believe so. Yeah, the X direction. So there's little things here and there that certain uh, certain mates can do to benefit things, especially when you have further constraints or further mates that are uh, already part of your assembly already. Some that we haven't really touched on would be like this profile center, and as I mean, it's kind of a vague name, but we can pick out bits and pieces of what it actually means. Really, all that it's doing is that if we take a specific profile, whether it be a face, generally speaking, we like them to be flat faces that are not um, limited in any way. So if I try to do a profile center on this top face, I wouldn't really like it because I kind of have this chip cut out of it. Think of it as something where you generally want to have a face that has a reasonable center point, a center that is easily accessible. Um, but you can kind of think about a profile center as almost like a coincident mate that also has this almost like concentric element to it. So I don't actually even have to ensure that both of the things are cylindrical in order for it to work. So essentially what's going to happen is if I select this face and this face here, and if I flip that mate alignment and hit select, well then now I can't move this at all. So there's no translation that I can actually give to this pin anymore. The only constraint that it doesn't have is rotation about the x-axis. And that's because the center of that circle at the top of the pin is now aligned with the center of this face of the of this box that we have here. I mean, I can try to do it with that top face up here, but it's saying that it's not a valid mate type. And that's likely due to this little cutout that we have here, because we know that this doesn't have anything of that sort. I can also bump that dimension up, so then it'll still be perfectly aligned with the center of that face, but instead it's just going to be 40 millimeters from that distance. Um, but I'm just going to choose it to be uh, 0 millimeters there. I don't care that much. I want it to be right aligned with that face. And then just so that we can further constrain this pin, I'm just going to make sure that this cylinder is vertical. So a way that I can do that is I can go back to my standard mates, and one thing that I haven't really described too much, but let's think of it like this. If we have a cylinder, that cylinder has to have an axis of rotation or revolution, regardless. Um, and SolidWorks can actually be a little bit clever or smart about this. So essentially, if I'm doing something like, say, a parallel mate, if I select an edge, well then, even though for something to be parallel, I generally want it to be two edges or two faces, I can select this inner cutout. And it's actually going to align both the axis of rotation of this cylinder with this edge here, as you can see right there. Or I can flip it perpendicular, so it would be perpendicular to that edge of it. So that's a nice little way that even though we know that we don't have something that is, uh, it has a proper edge that it's a part of, and I mean, we don't have any linear edges on this pin, it's almost like a linear edge that is embedded within the geometry already. And now what I want to do is I actually kind of want to put this yoke on the adjusting pin similar to how we had it before, but I want to do something a little bit different. And I know there's no threading on this pin, nor is there threading on the inside of the yoke, but uh, adding threading tends to be a little bit trickier, so we're not actually going to work with any of that. I want to use something different, something that we haven't really touched on too much. I want to use a screw mate for this. And kind of what you might expect is that for a screw mate to work, kind of similar to a concentric mate, we want to have two cylindrical faces. So I'm going to select the screw mate, and I'm going to select this first as our option, and then I'm going to select this here as well. And you'll see now that we have some details. You'll see this arrow here that's indicating that we're going counterclockwise. And we also have some information here on the left-hand side. One of the options that we have is revolutions per millimeter, and the other option that we have is distance per revolution. So these are little important details that you might get regarding some sort of geometry or some sort of a sketch where you need to look at that and you need to say, okay, well, this, if I'm given information like this isn't something that's just sliding on. It's actually taking rotational motion and translating it into translational motion. So let's just say that I want this to be not 20, but maybe like 5. Um, I want it to be less than that. So let's actually see what 0.5 does. Half of a rotation or revolution will give me 1 millimeter. Just because I know that since millimeters are smaller, it might take ages for this to actually wrap around. And I'm going to hit select, and we'll see what happens. So I can't push or pull this. You see that it's only rotating now. And it's actually rotating right along that axis. And if you're kind of looking carefully, you'll see that it is, in a way, threading onto that pin there. And I can keep doing this more and more and more and more and more. But you'll also notice something. When I was out here, it wasn't even attached to the geometry. And in fact, just so this goes a little bit quicker, I'm going to change this to a quarter revolution per millimeter, because it's going to be painful to try to do it otherwise. There we go, that's at least a little bit better. Okay, so now it goes a little bit better. Um, but you'll notice something here in just a moment. It goes right through that pin, and we don't necessarily want that. So generally speaking, whenever we have a screw mate, we have to pair it with a different type of mate, or another mate that we have used before. We probably want to pair this with a limit distance mate, because that'll ensure that even though it's rotating, there's still translational motion that is happening here, which means I want to make sure that between here and here, so try to do like a coincidence, not, it's just putting it at 1 millimeter away. I want them to be able to touch if possible, but I want it to only reach around here, which I think was around 40 millimeters. It might be a little bit less, but just for the sake of ease, I'm going to bump this up to say like 15. So it can only have a max distance of 15 millimeters, but a minimum distance of 0 millimeters, which means that those faces can touch. However, there's only so much that I can rotate it out. So you see if I start kind of moving it a little bit, once I get here, if I start pulling on it, it's not doing anything. It's not actually moving any further. But if I click on this face and then start moving it outward, kind of slowly, it's a little bit janky. And you'll notice that it does that sometimes if you move it too far, it'll snap it to another reasonable position. But you notice that when I get right here, I can't move it any further. It's stuck, which is exactly what we want. We don't want it to go any further than that. If we actually check what this distance is, sure enough, it tells us that that normal distance is 15 millimeters. So we know that the combination of that limit distance mate along with that screw mate do work in tandem with each other. They actually work very well uh, with each other. So it's always kind of a good pairing of mates if you're going to use something like a screw mate. Um, so try to keep those things in mind that there could possibly be some other mates that you might have to look at or take into account for this upcoming exam. Something else that may or may not be on the exam, but I think it is a good thing to keep in mind is, let me see about duplicating that adjusting pin there. And I'm actually going to edit this geometry here a little bit. I kind of want to get rid of this cutout, and I want to add some hole wizard holes, and you'll kind of see why I'm doing that very shortly. So I'll go back over here. I think it was this cutout here. I'm just going to suppress this because I don't want it there anymore. But I do want to add a couple hole wizard holes, maybe just like 2 or 3, just to make life easy. So I'll position things. I'll say that I want to sketch on here, and maybe I'll do one over here and one over there. And then I'll smart dimension them appropriately. Something like that. Then I'll just say that all of these are horizontal with each other. Cool, and now everything's fully defined. Remember to always fully define your stuff. Um, okay, cool. For whatever reason, it didn't take. Let me do that one more time. I'll just do, yeah, I'll do 30 still. There. And just do this guy. Sure, whatever. I'm not entirely sure why it's not showing up with anything. Oh, there we go. For whatever God knows reason. So let's do a countersunk or countersink head ANSI inch. We'll do metric. Yeah, we'll do metric. We'll keep it as a flathead screw, and let's bump this up to like something possibly of reasonable size. I don't know why those are so tiny, probably because this is such a large face here. And then I'll just increase the diameter, or increase the depth rather. Let's just say that it goes down 40 in this case. So it is a ANSI B18 67M and an M7 size, normal fit. It goes down 40 millimeters. So I'm not going to hold you to remembering any of those specifications. That's not what I'm after right now. And I'll just hit select. I'll probably also get rid of that internal circle, or cylinder, just because I don't want it messing anything up. And then I'm going to go back to the assembly. So I just wanted to make that small edit because now things will be a little bit better. Now I can stay within here. Um, the first thing that I'm actually going to do is I'm going to try out this other option that we have here. This is called a Smart Fastener. So it's in your assembly menu. It's kind of, what is it, like fifth from the left-hand side. And it looks like a little folder with a lightning bolt and a screw or a bolt right on it. And this is actually very helpful. So requires solid, okay. I need to add the toolbox to this stupid thing. There we go. So this is actually very helpful because now that I have my toolbox added, if I select Smart Fasteners, it's going to yell at me for a second. It's going to say something along the lines of taking extra time. Uh, just ignore it and just hit OK. It'll allow you to just continue. But now we have this menu where I can select certain faces or geometries to populate with the appropriate screws. So assuming that you did use the whole wizard, you're actually able to just directly assign specific bolts to those given regions. So I'm just going to select this face here, and it recognizes, hey, we have countersunk holes. It's an M8 flathead screw. There's other details that are also a part of that screw, but it's going to be able to fill in the gaps. Having this information right here is pretty good on its own. So when I hit add, I think it's going to yell at me one more time. Oh, no, it actually doesn't. Surprise, surprise. So it's almost as if we went into the correct location where this information was and just drag and dropped those screws into the appropriate location. So we'll see now it's giving the correct fastener type. It's a flathead screw ANSI B18.6.7M, which I'm pretty darn sure is what we had for the whole specification. I can definitely check that one more time once I get out of this, but that sounds about right. There's some configuration name information down here as well, but we'll kind of get more into that in a second. And I believe I set it to be 35 millimeters. It was either 35 or 40. Those are little things that we can check, but we can also do a cross-section view. So when I hit OK, well, now I've populated it. So you'll see that these are technically underdefined, just like how they would be if you just added them into the assembly itself. But you can see it added those coincident, what is it? Those coincident mates. And it's simple enough to just go back into my mates menu and then say, hey, I want this edge to correspond to that one. I want them to be parallel. Similarly, I want this edge and this edge to be parallel with each other as well. And when I exit my mates menu, now we can see that that flathead screw is indeed, both of them are indeed fully defined. Oh, that was the other adjusting pin. So this is a nice little way that we can sort of be able to just add those fasteners to our geometry without having to do really much work at all. And we can see here when we look at it, it goes the appropriate depth. So the reason that it doesn't fully go down is because I'm fairly certain for these flathead screws, they have a flat base as opposed to having a pointed end here. And I'm pretty sure that there was no 40. I think that this was 40 like I had mentioned. However, there was no 40 millimeter screw that SOLIDWORKS had within its toolbox. So it just chose to click the or select the next best thing. So this is a really nice way that we can add certain bolt features without having to really worry about digging through the toolbox for ages, trying to find the correct thing. I wouldn't say it's something that you should rely on, but it's very good if you want to just quickly get an indication of, hey, I have hole wizard holes here, or there's supposed to be bolts in this location. Find it for me. Tell me what I should be looking for. So this is quite helpful. And what I'm going to do, just because it'll be relevant a little bit later, is I'm just going to assign these both as some material, presuming it lets me. Let's obtain right axis. Great. Maybe if I do edit. Are you still going to yell? Nope. Okay, it actually worked that time. So I just assigned these to be 1023 carbon steel sheet, which isn't really that important right now, but it will be important once we get into some of the further details regarding what is it? Regarding the bill of materials. So if I exit out of this cross section and I just rebuild things just so that everything is all happy and dandy. So we still have this guy. It can rotate just totally fine. I guess you can define fine because it's a little choppy. You just kind of need to be a little bit slow with it. This is something to kind of keep in mind that you can have those the screw mates and the limit distance mates to kind of go along with each other. Another thing that we haven't really talked about too much is rack and pinions, which there is a specific mechanical mate for it. I know I went very briefly over cam followers, and that's not going to be too relevant, but they are interesting, so I can go more detail into that possibly another time. But I do kind of want to get a little bit or talk a little bit about rack and pinions. So not only do we have um, just nuts and bolts, bearings, O-rings, but we also have other things. So power transmission, and power transmission is going to be things like your gears. But what's nice is that not only does it have things like bevel gears or helical gears, um, but it also has rack and spur gears, or your rack and your pinion. So I can, just like I would before, I can add these just directly to my geometry, or to my assembly rather, and kind of play around with the settings here. So we can see that now we have this rack, And I can add an appropriate spur gear to this as well. I'll have to do that once I exit out of this menu. And it's saying, let's do like a length of 200, why not? Just so it's a little bit longer. And then I'm going to add a spur gear. It wants to add another one here. Can you let me leave? There we go. I'll add a spur gear that's relatively speaking the appropriate measurements as well. And just so that it's this gear can fit on this pin, just to be able to do so, I'm going to designate that it has a nominal shaft diameter of 12. I believe that's what it was in this example here. So that's good so far. I'll hit OK. And I could add another one, but I'm not going to. And I'm just going to start mating a couple things together just to kind of set the stage a little bit. Probably make things a little bit easier. I'm not going to go too in depth with this one just because it's not as relevant, and I haven't gone over spur gears enough for me to feel comfortable to put something like this on the exam. So don't worry about this as being an exam topic, but I think it's just something that's important to be uh, to keep in mind. Um, so I'll show it in that direction. I'm also going to make sure that this pin is aligned with one of these sides. So I'm just going to do a parallel mate between the axis and that edge, just so that they'll always be in the same line as each other. And I'm going to start mating a little bit of this rack and pinion to the top of this block. So I'll say, well, I want an edge mate here and hit OK. So that means it can slide, but it can also rotate. And I don't necessarily want it to rotate, so I want these two things to be coincident as well, and certainly not in that direction. I want it to be like that. So this is pretty good because now I can still rotate this, or not rotate it, but move it back and forth. It is allowed to move, just like how we want it. And then I'm going to see if I can at least move this into a reasonably appropriate location. Maybe have it something like this. Okay, we're doing kind of okay. Now I want to make sure that it is moved over appropriately. And I'm just sort of going to try to fit it at about right there. Um, these are a little bit funky. I haven't really looked too deep into making sure that a rack and pinion works very proper, and that's why I'm not going to have an example like that on the exam or a question like that on the exam. Um, so don't worry about that. But what I'm going to do is I'll fix this adjusting pin just so that it's, I mean, it is floating, but at least it's static. And I want it such that when this rotates, this rack is going to move as well. So I can go back into my mates, and if I go into mechanical mates and hit rack and pinion, well then I can select an edge of my rack, so it can just be this linear edge. And you kind of want to consider your pinion gear selection to almost be like something that would be rolling along the face or rolling along that edge. So I want to select this inner edge if I can. Here's what I might actually do. I'm actually going to hide this pin first, just so that I don't have to worry about it because it's annoying me. And I can go back into my mechanical mates, select rack and pinion. My pinion can be this circle here. My rack can be this edge here. And I'm not entirely sure how to get the correct uh, pinion pitch diameter or rack travel per revolution right off the bat. But if I hit OK on this, you'll notice that it isn't working appropriately. The rack is moving more than the pinion is. Uh, but they are working in tandem with each other. So it is creating translational motion from rotational or vice versa. I mean, I could probably play around with this, like if I change that to say like 1 millimeter. Oh God, That might be a little bit too little. Maybe if I try something like 10 or perhaps 13. I think I had it at 12 before. That looked good, but it still is going a little bit too fast. But that's the general idea behind the rack and pinion. It's taking either rotational motion and turning it into translational or vice versa. And I can unhide the adjusting pin. I can show it one more time. It says that this is still underdefined, and to solve that, if I wanted to, I could just say, well, maybe I only want it to have a maximum distance from here to there and a minimum distance where these sides are aligned here. And that would more than likely fully define everything that we need here. Okay, so I covered those things. I want to talk a little bit about the bill of materials now. So in order to do that, I'm going to have to create a drawing. So let me go to File, and then I can hit Make Drawing from Assembly. And now I have this that I can just input in here, so an isometric view as we normally like to have. I could add an exploded view over here, but I don't want to go through that right now. I feel like there's at least reasonable enough information on the exploded view stuff, unless somebody has a question about it once I'm kind of done going through the bill of materials. But I will just make sure that this is a shaded in high quality view. I'm not going to play around too much with the sheet settings here. That's probably too large. Yeah, I'm going to change this. And you can change the custom scale as well. So I know on my end and possibly your end as well, it probably shows 1 to 1, 1 to 2, 1 to 5, 1 to 10. If you are using this custom scale on the left-hand side, you can adjust that as well. Let's say I wanted it to be 1 to 3 instead and shrink it. Or perhaps I wanted to shrink it even a little bit more. Maybe I wanted to do, well, that's not right. Still 1 to 3, but if I wanted to increase it, I could change the ratio even more. So I could change this to 1 to 4 if I wanted it to be a little bit smaller, but not too small. But I kind of like it at a 1 to 3. That looks pretty good without taking up way too much space. Now, obviously, we can't see everything here, but that's not really the point. So if I want to add a bill of materials, one way that we could do it is we could go through the Insert and then go to Tables menu, but there's actually an easier way that's directly on this page. If we're on Annotations here, this third from the left Annotations tab, on the far right-hand side of it, you should see something that says Tables already. When you click on that, the third from the top should be a bill of materials. So it should allow you to get this info on the left-hand side here. We're not changing anything, so we're just hitting select. And now I can input this bill of materials into our drawing here. And I'm actually going to shrink this just a little bit more just because I don't want it to be covering up uh, important stuff for the sake of this bill of materials here. So it is covering up some quantity options here. So I might change this to 1 to 4. I wonder, what would this do? Probably too big, yeah. Definitely not that. So we'll keep it at a 1 to 4. And I can just move it a little bit more off to the side. Okay, so we have our bill of materials here. However, this description tab is fairly useless. It's completely empty. It's not doing anything for us, and we don't really need it to be a part of our bill of material. So I know that some other people or some other TAs might have some of their students adding like the mass and the density and this, that, and the other to it. And it's like I just want to know what the material is, and that should be good enough. So I know that this was kind of a bit of a process last time, so that's why I want to go through it a little bit slowly, especially considering on my end a lot of the windows that you guys end up seeing, if they're not just innate to SolidWorks, it won't actually pop up, which is fairly stupid. So I'll try to be as descriptive as I possibly can about what I'm seeing on my end to make sure that you guys are able to replicate it if you do. So if, where am I going? If we go back to any one of our given parts, um, so say if I go back to, and you might be able to do it in the assembly itself, but I'll just show it from one of our parts that we already have, the adjusting pin. One method of going about this is that if we go into our configuration tab, we'll see the configurations similarly like how we would see them in the assembly. And if we right click on default, one of our options in the middle of the menu should be properties. And I'm fairly certain you don't even need to go through like those several menus to get there. I've noticed that at the very top, kind of near your rebuild option, there should be something that says file properties. And I'm almost positive this is the identical menu. So I'm going to do it here, and then I'm going to see what sort of information probably pops up in the assembly as well, because that might make things actually overall easier. So if I go to File Properties, then it'll open me up directly to the Custom tab. And like I said, you guys probably aren't able to see it on my end, and it's stupid and not showing up on the recording, but it basically should show something that says summary information with three separate tabs in it. One is summary, one is custom, and one is configuration specific. We want to be in the custom tab. And you know what I might actually do? I might see if I can do something like this. Okay. All right. It won't show up on the stream, but it'll show up on the recording. So if you want to go back around this time on the recording, I'll see if I can put like a timestamp on it because you should be able to see what's going on now. Basically, we have this menu here for the summary information. And what we can do is into the property name, I'm going to put material. So material. So for material, I can then specify the type, which if I remember correctly, I believe it was just staying as text. And then for the value of this, in the first drop-down selection, it should just say material. And then I can just hit material on that. And it should give me all the details where in the property name, it says material, in the type, it says text, and in the value/text expression, it should say like SW material, blah, blah, blah. And in the evaluate value, it should be specific to what that material actually is. And then I can hit OK on this. If we go back to the bill of materials now, or rather the drawing over here, I should see an option pop up. So if I click on C, where you see this little arrow pointing downward, I should see some options up top here. And this top one right here, it's basically like third or fourth from the right-hand side. It should say Custom Properties. It's right next to one that has a little eye as an indicator. When I hit that, now I'll actually have that material selection available to me. So once I hit material, it will populate it with that adjusting pin material, that 1060 alloy. And when I click out of it, now it's there. Now, I am a little bit curious if I can pretty much do all of these just directly from the assembly, because we can see that we have the same option available to us right here. And it's actually, unfortunately, very stupidly not showing up with that custom property as well. You might be able to do other stuff. Material. So you might be able to do everything from that menu, but let me actually test it. Material. No, it doesn't actually work. That's kind of dumb. So unfortunately, you can't go through that process just on the assembly itself. It has to be on the individual parts themselves. So this will require you to have uh, the parts open as well. But you can go into each of those individual parts. A nice thing is that if you have the option to do so, you're able to have several of those parts open at once along with the assembly, and any glaring changes that you might make to a specific part will just require a rebuild of the assembly itself. So similarly for this, I can just go back into that, what is that button called again? That file properties button. And when I select that, then I can basically just do the exact same thing. So I can hit material, if I can spell correctly, text will input properly, and then for this I'll specify, hey, I want it to be the material of this option here. It's an AISI 1020, I believe it said. And if I go back to my assembly just to double check, when it reloads, lo and behold, it does show that value there as well. Now, in terms of doing this for any of your bolts or any of um, your toolbox parts, I don't know if it's actually possible to do it for that. It might be, but I'm not sure off the top of my head. I would probably speculate that the best way to check would be to say, well, I'm going to select my flathead screw or one of my flathead screws from the feature tree and then try to keep that selection going. So currently it says that that is selected, but I'll just say, well, I want a material, I want it to be text, and I want it to be material here. Yeah, but it continues to try to do it for the entire assembly as opposed to um, that part itself. Uh, and I'm not entirely sure if it's possible to be very specific about it. Maybe in this material, in the configuration specific tab, but I'm really not sure. Material at default. Apply to, yeah, that's for configuration, so that doesn't actually help. So in an instance like that, for any of the bolts, I would just write them in. And it's going to yell at you when you try to do that, but that's okay. I think we're all used to it by this point, SolidWorks yelling at us. So this is 1023 carbon steel sheet. I might see if I can, nope, I can't. So I'll just try to remember that. And that was for the bolts. So for these guys, yeah, it's going to say that it's linked to a property in some sort of read-only document. Do you want to break the link? Yes. So you can break the link when it comes to toolbox components because, as I said, I don't know a good way of doing this otherwise. So this was 1023 carbon steel sheet, if I remember correctly, and it was SS. And then that'll just populate for that information appropriately. Um, so for the rest of these, we could obviously assign measurements as well. For any of the parts that I end up giving you, um, I would like I would like those things to be I would like all of those to be those materials to be assigned from that file properties manager. Um, Otherwise, if it is a toolbox component, you can just write it in. Like I said, it'll scream and shout about it being linked to a read-only document. That's totally fine. It's not something uh, that is worth a fuss. So I mean, if I wanted to say that this rack had a material of, let's say, like chrome stainless steel, and I hit apply and OK, well then I would just write in chrome stainless steel for that rack. So over here, I would just double click on that box and then just put chrome stainless steel and then just select. So should be all good beyond that. Now, in terms of some other details that I remember I had briefly mentioned, specifically regarding kind of information that's given, excuse me, for a specific bolt. Let's actually go a little bit into that because I think that that'll be important at bare minimum just to understand sort of what is going on. Um, so if I go to that, and then let me just duplicate one of the bolts that we already have. So I'll just hit Control and then click and drag one of these bolts away from it. So now we have this, and I'm actually just very briefly going to go back to our in-class assignment 7 where I added these extra holes here because I want to just look at all the different specifications that we added to it. It'll just make things a little bit easier to kind of compare and contrast. So we said, kind of I figured, we have a hole depth of 40 millimeters. It's a size M8. It's an ANSI metric, so anytime you see an M and then a number following it, that's your indicator that it's going to be metric. If it is an inch, it's going to have some sort of pound sign or number, either a number with a pound sign or a fraction there instead. So these are all like 9/16 of an inch, 5/8 of an inch, quarter inch, 5/16 of an inch, anything like that. Um, but these ones here, whenever there's that M in the front, that's indicating a metric measurement. And it is a flathead screw ANSI B18.6.7M. When we hit OK on that, if I go back, and then I want to just look at the details for this pin, or rather for this bolt that we have here. So I believe it was this one, and I'll just right click and I'll hit Edit Toolbox Component, make sure that it shows up, and let's kind of compare some of the details that it told us in that Hole Wizard specification and here. So on the side, it's an M8, which I didn't assign this from the toolbox. I assigned this just from the Smart Fasteners option, which I talked about a little bit earlier. It's a length of 35. And we might be asking ourselves, okay, well, why is it a length of 45 or 35 instead of 40 here? Like the hole was 40. Well, I could make it 40, but let's actually see what happens. You might already be kind of understanding what I'm getting at here, but let's actually just check it. If I edit the toolbox components of these two, both of which could be a depth of 40, they were 35, but now if I select them as 40 and I hit OK, let's see what happens when I do a cross section. That looks like a little bit of trouble, because you can see right here, this is some interference going on right there. So true, it could be, or could have a total length of 40 millimeters, but because of the angle at the bottom of this shaft, it's just going to go right through, because it doesn't have a conical bottom to that screw. It just has a flat bottom to that screw. So it's, I guess the long and short of it there is it's better to be uh, less deep than more deep to prevent any sort of interference that could end up happening. If we go back to this, and then we can talk a little bit more about some of the specific toolbox information that's here as well. Well, let's see. So if we're looking at the configuration name, this gives us a lot of detail as well. So we know it has a length of 35, and it also has a thread length of 35, so that means it's totally threaded throughout I think the entire shank of the screw. I can show cosmetic to just kind of verify that, so we can see that the threading is on the entire screw here. And then let's sort of go through some of the bits and pieces of this configuration name here. So we have that first part that we saw before where it was the B18.6.7M. All of those details that I just said, that mouthful there, is all exactly the specifications that we made the hole. The M8 is the size of the screw. The 1.25, I'm actually not sure what that is. I think that is the head diameter. And the 35, this 35 is specific to the length, not the thread length. And the reason that there is a difference there is because of this very last measurement, or rather this kind of specifier right here at the end. So you might not have seen it or been paying attention, because I wasn't making any attention to it, but this used to be an N here instead of a C. And the reason for that is because it was simplified. So there are different specifications even for how the thread is being displayed in the model. A simplified thread will always show up as N. I don't know why. I think that's just basically saying normal or nominal or something of the sort, where it's giving a nominal diameter of the screw, which just means what is standard, what is typically seen, quote unquote, out in the field. Uh, C, as you might expect, is for cosmetic. And S, I believe, yes, is schematic. So we can see, I know I had already shown this before, but this schematic screw is showing you effectively what that screw would look like in quote unquote reality. Uh, if we're being honest here, it literally isn't even like a helical thread. It's totally cylindrical, so it doesn't actually translate downward at all and around. That being said, that would be very difficult to do. And that's not to say that you can't add those sorts of things in SolidWorks. I think this is just a way of uh, ensuring that you're not going to get too much complication in your model. Um, Say you're doing things like simulations, having a realistic thread is already going to make your model reasonably complicated, which means adding even more detail to it could make things that much more difficult to work with. So that's generally speaking why it's not an even more descriptive cosmetic thread that you see there. And that's generally speaking the breakdown of all the different things that you will tend to see for those specifications. If we go back to the page here, all of those details are right here as well. So literally everything in that configuration name that you saw at the very bottom, if you are adding a toolbox component, is listed right here in the part number. I don't know why it says part number. It's probably better to say part name. Okay, fine, all caps. Um, I'm not going to be picky about how this is labeled, so long as you have these four things here. These are what I am after. I'm after the item number, the part name or number, however it wants to stupidly say it, the quantity, and the material. So if you have those four things in your bill of material and they're all filled out, everything is good, then I'm a happy boy. That's what I am after. So hopefully anybody who is watching right now and is watching later um, and at least reads the details that I've placed kind of on the exam questions once you guys take a look at them tomorrow. Hopefully everybody is on the same page with that. I don't want anybody saying that I never said it. It's on the record. Um, I think that is just about it. Okay, thankfully, because that wasn't. It was a little bit longer than I thought I would be going, but I mean, at least it was a fairly reasonable time, just short of an hour. Uh, I can't think of anything else that I really wanted to go into detail through. Hopefully this wasn't like too disjointed of like a little mini lecture or recitation. But if, I mean, I'm done. So you guys, if you have any questions about anything that I didn't go over, just so that I can keep the recording going for anybody else that might have similar questions, shoot. I'm all ears. Just some other basic, what are the various things we should be doing for the test? So like what the test, like what the questions will encompass? I think that's the question you're asking. Oh, I see. Um, so have a very good grasp of all of your standard mates. I would say that at the very least. Um, your standard mates should be your bread and butter. And I'm not going to say that they're super easy or super rudimentary mates, but they're the most basic ones that we can have with very general geometry without having to get into really nitty gritty geometry where you see things like the rack and pinion where you have to mate an edge to a linear edge to a cylindrical edge. Um, like those, like your standard mates don't encompass those sorts of things. So if I just look at the mates menu, know how to use pretty much all of your standard mates. And I will say this right now. Do not use the lock mate as best you can. Um, as far as I'm aware, this is kind of a cheap way of doing certain things because majority of the time you can fully define something and you're fully define one or more components without having to ever use the lock mate. The only thing that is similar that I would like you guys to do is make sure that in your assembly you have at least one thing, and I would say at most two, but there should be no reason for you to have two fixed components. You should have one base component that is fixed, and then all of your other components should be fully defined based uh, on that common component, which has common mates attached to it. Locking mates together or locking components together via a mate, it's why don't you just fix the component? I mean, it probably does function a little bit different, but there's really no situation where you significantly need to lock things. So I would say have a pretty good understanding of all of these standard mates, excluding lock, or I mean, you can have a good understanding of the lock mate, but I just wouldn't use it. Um, in terms of your advanced mates, the ones that I went over today are are good. Are a lot of the ones that you will need to consider. So anything that I really didn't go too much into detail about, I wouldn't worry about. So linear coupler, there's not going to be anything on linear coupling or anything on path mates. There might be some stuff that requires you to think about width or profile center, or the limit distance and limit angles. Those are very important. They outside of your standard mates, limit distance and limit angles are probably some of the most important ones as well. Um, understand how the mate alignment stuff works. And in terms of your mechanical mates, I think I mentioned it before. Don't play or you don't need to worry too much about a cam mate or a universal joint mate or a rack and pinion mate because I didn't go too detailed into the rack and pinion as well. Uh, understand hinge, understand slot. Gears are okay, but you don't really need them just because that's more detail than I want. Screw mates could be very important as well. So consider, like I said, consider a lot of the different mates that we talked about during this little recitation. In terms of creating parts, let me see. Um, have anything sweet boss, lofted base, ribs. So, like I had mentioned about how the uh, how the exam is going to be structured, one of the problems, the first problem, oh, excuse me, the first problem, you don't have to make any parts. The second problem, you do have to make simpler parts. So I would come prepared and understand how to use things like Sweet Boss and Lofted Base and Rib and some of those advanced functions, um, but I wouldn't rely on them too much. Uh, from my perspective, I've already sort of tested a lot of that for the first exam, which is more so your guys' understanding of all the different features. Um, this I am going to be more focused on the assembly and drawing side of things. So I would still say have a good understanding of those things, but I wouldn't say it's something that you need to uh, come prepared ready to do. I guess that's probably the best way that I can phrase it. Know how to use them, don't expect to see them. Just because, and the reason why I kind of want you guys to still have a good grasp of those things is because there is a very real chance that you will use um, a lot of those features for your guys' final project. And I know I'm late on it. I'm going to try to assign groups um, tonight. So there's going to be about 5 groups. I think 5 groups where you guys. I'll be putting you in groups. I'm kind of creating them and playing around a little bit. So I'm sorry, they will be assigned. Um, Sometimes we don't always get to choose who we work with. But as a little precursor, I think I posted a bit of a rubric up on Canvas already. Um, I don't care who you're with, or rather, like whoever you're with. I want you guys to be working together. I want you guys to be talking about things and interacting. I don't want one person doing all the work. I know how that crap happens sometimes, where it's like one person does the entirety of the project. I know there's a good handful of people in this class who probably could do the entirety of the project by themselves. Try not to do that if it's you or if it's someone else that you might be working with. Try to collaborate and talk about things and kind of bounce ideas off one another, because if one person's doing all the work, not only does it suck for that person to do all the work regardless of whether they want to or not, but it makes it so that the other people don't participate, and then they're not learning anything. And then I'm looking at that from the perspective of, well, if these 2 people did all the work, were they doing it just because they wanted to get stuff done, or were they doing it because everybody else was slacking off? How am I going to ensure that the people in those groups are not just getting a uniform grade based upon one person's work, but kind of assigning things based upon the merit of the work, and upon the merit of each of the individual people in the group. And I'm not going to deep dive. I'm not going to like say, okay, did you do this, 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 and this? But I'm going to ask you guys near the end or intermittently and say, are you guys working as a team? Are you splitting up the workload? Are you making sure that one person isn't doing everything, or people aren't slacking off? Because I want to make sure that that's not happening, because if it is happening, then it doesn't seem fair, in my opinion. It seems like if one person is doing all the work, then the other people don't necessarily deserve the same grade. So participate, work as a team. It's not going to be the first time that you guys probably have worked as a team. It certainly won't be the last, especially if you continue on in your career of engineering. So use that to your advantage. Um, Anything else? Um, all right, guys. Well, it was nice seeing a couple people who showed up. This is going to be on YouTube very soon, so I'll make sure to cut this recording here in just a moment and then post it on YouTube just for you guys if you want to go through it one more time, or for anybody else who wasn't here anyway. Thankfully, it was only an hour this time instead of like 3 hours worth of stuff to sift through, so hopefully it goes a little bit quicker if you guys want to review this later on. Um, I have work in a couple of hours, but I'll be home after about like 8:30, so if you guys still have any questions about anything, anybody who's here in the lecture right now, or anybody who might show up or watch the recording later, um, just let me know. I'll be available tomorrow as well. So once you guys start the exam, it's going to be kind of like what I mentioned. You start it, and that time for when you start it, you have 6 hours to complete it. So it'll open the second it hits the 19th, and you guys can crank it out in those 6 hours whenever. So uh, good luck when you end up taking it, and hopefully I'll hear from any of you guys if you need any questions or clarifications with anything. All right, cool. Take it easy, guys. Good luck.